Also, you can also write linear equalities in that ax plus by equals c, otherwise known as standard form. 3x minus 2y is greater than or equal to 12. I'm making these numbers up. So in this case, m is slope and b is the y-intercept. Y mx b. In this case, opposite of whatever a divided by b is equal to slope. Just a real quick reminder on those couple of things. Most of what we're doing today is identical to what you've done already with respect to slope and solving these linear equations. But now they're not equations anymore. They are inequalities. I want to bring your mind back to something I remember Ben asked about. This was a graph from like lesson 3.5 maybe. Recalling that these were equations, right? And the answer lies on the line for this particular equation. And the answer lies on this line for this particular equation. Where those two lines intersect would be the answer that would satisfy both. The only answer that would satisfy both. What you're going to see today continues with that thought. And in the book, I just want to make a point of this. Here's an example of another graph of an equation. You guys have it, so I know it's not real clear. But this equation, which is y equals 1/2 x plus 1, is satisfied by the numbers that live on this line. Okay? Then any points above it are perhaps larger than this equation. Points below it are smaller than this equation, which when you graph it looks, and again I know this is in your book, but before I just want to introduce it a little bit, that means anything greater than is the stuff that lives above it. Anything less than is the stuff that lives below it. Now, as far as the line itself, do you guys notice how it's a dotted line? If you can't see mine, look in your book. The dotted line is utilized when the inequality is less than or greater than. The only time you will utilize a solid line is when it is less than equal to or greater than equal to. And we're just going to start looking at these and sampling some of these real quick. So less than equal to, greater than equal to are solid lines. By the way, the names they utilized for less than equal to closed half planes. This is a closed half plane. This is a closed half plane because it's less than equal to, or greater than equal to, less than equal to. The other one is called open half plane. Greater than or equal to, dotted line, less than or equal to. All right, we can put these to work. My example 1 is going to start like this. Graph 3x minus 2y is less than or equal to 8. All right, based on the brief, quick introduction, do you believe the line will be solid or dotted, and why? Solid, because it is less than and equal to. It is the equal to thing that makes you have to also utilize the solid line. Okay, so now that we've established that, we can start considering the graph of this particular inequality. What I like to do is convert these into y equals mx plus b form. Again, this equal sign is kind of irrelevant. I know this is my symbol, but in any case, I like to use slope-intercept form. To convert this to slope-intercept form, I want to isolate y on one side with the x and the number on the other, and then kind of keep it in that particular order. So it's negative 2y is less than or equal to negative 3x, and that was a positive 8. Positive 8. Here's where I'm going to aggravate everybody. In inequalities, whenever you divide by, or multiply using a negative, so this is a factor slash divisor, if it was a division situation, you must flip the inequality symbol, which would look like this. Divide everything by negative 2, because we don't want negative 2y, we want y. Y is mx plus b. So now I've done that, y. That flips. Beautiful, greater than or equal to. Negative 3 by negative 2 is a positive. Negative 4. Okay. Now we're going to graph this. Okay. So here's my example 1. Y is greater than or equal to 3 half x minus 4. Graph it as if you're just graphing 3 half x minus 4. So 1, 2, 3, 4. Here's your y-intercept. Y-intercept is equal to negative 4. How do I know that? Because it tells me it is. Your slope, the numerator, if it is positive, means you go up. If it is negative, you go down. So we're going to go up 3. Boom, boom, boom. Denominator, you always go right. So far, so good? It is a solid line. We already established that from the get-go. Okay? We graphed it. The final step after you have graphed it is to shade the correct plane or area, I heard somebody say. Beautiful. So which side do we shade? Now you all might be thinking, well, it says y is greater than or equal to, so I should probably just go ahead and shade this, and you probably are going to be right some of the time maybe. The better way to ensure that you're correct is to test a point. I love, whenever I can, to test the origin. If it's on the line, you can't. But if it's not, you can. So I'm going to test 0, 0. If 0, 0 is true, then this is the side I shade. If it's not true, then it has to be the other side. Okay? So we're going to test 0, 0. And I'm going to go back to the y is mx plus b form. It's easiest for me to test. Y is greater than or equal to 3 halves times 0, which is 0, minus 4. Is that true? Yeah. So since 0, 0 is true, we're going to shade that portion. Just like that. Doesn't have to be pretty, however you prefer to do it. Some people do the side of the pencil thing. Those of you that have art class are probably going to have real pretty graphs. Okay? Since 0, 0 is true, you shade the plane including 0, 0. If it weren't, we'd shade the other side. Not too shabby, right? Guys, this is everything we're doing today in a nutshell. The only thing that gets tougher here as we progress is some of the various transformations that we have to make to get our inequalities to a place where they're y equals mx plus b, shade, that kind of business. Okay, so I'm going to go ahead and continue with example 2. Here's example 2. The only thing about example 2 is that you have to maneuver a number. Well, no, I guess you don't. Actually, guys, do me a favor. Look at the book example 1 real quick for 1 second. Notice how it's greater than or equal to 0. They subtracted the 4. And then the rest they went on with, okay? Okay. So let's get going. Example 2. Graph. And it's just another pretty little system. All right, here we go. 3x minus 2y is less than 6. We're going to solve it and graph it. Okay? Step 1, based on what I was trying to describe, get it into y mx plus b looking form. Again, that's not it's the thing you want to worry about. We're going to maneuver our 3x to the right, which gives us negative 2y is less than negative 3x added to 6. Dividing by a negative means we need to flip our inequality symbol. We have the same slope as last time, don't we? Mm-hmm. Yeah. All right. Y is greater than 3/2 x minus 3. Oh, I forgot to ask, will our line be solid or dotted, and why? Dotted, because it's not equal to. Because not also equal to. So we know we've got a dotted line, okay? We know we've got a dotted line. We now have an inequality that is graphable, okay? Let us pull out our paper and start by the graphing. Here we go. Example 2. Y is greater than 3/2 x minus 3. Start at a negative 3. 1, 2, 3. It's the exact same line. Yeah. Okay. That's hysterical.
Well, it's not exactly the same line.
Yeah.
It's a little bit in a different spot.
Up 3, right 2. Okay. So here's the y-intercept. And here's the slope of 3/2. Dotted line. I highly recommend you grab a ruler or some form of a straight edge for yourselves, because otherwise it makes my job very difficult to read what your graphs are. Okay? What I generally do too when I graph these is I will write what it is. Y is greater than, I forgot to do that with the other one, 3/2 x minus 3. Shading, we're going to test 0, 0. Why? Because it's not on the line and it's easy arithmetic to do. 0 is greater than negative 3. 3/2 times 0 is 0. Is that true? Yes. And there's your shading. We tested 0, 0. Because 0, 0 was true, we shaded the plane that included 0, 0. The ones that are deceptively tricky but not really, look like, let me see here. Trying to find something fun. All right, here's the next one I'm going to do. This is my example 3. Y is greater than 2. No solving necessary. Y is greater than 2. That means find where y is 2. Y is 2 anytime you go up 2, right? Would you agree with me? All of the points that lie right here would be y equals 2, right? Okay. Y is greater than 2 will be all the points above it. You don't even have to test anything. Oops, kind of lost my line there. Y is greater than 2. Dotted line, I don't even have to test because I know a 3 is bigger than a 2, a 4 is bigger than a 2, and everything above that. Those are all bigger than 2. Okay, there's my example 3. Example 4 and 5 have you considering systems instead of just single inequalities. Example 4, something like this. 2x plus y is greater than 1, and x minus y is less than or equal to 3. All right, I'm going to graph this system, and the way I'm going to do it is the same way I've done the other ones. First of all, this is going to be a dotted line. Would you agree? This one? How about this one? Solid. Let's get our y is mx plus b. Y is greater than negative 2x plus 1. Am I okay with this one?
Negative 1.
No, I didn't have to subtract the 1.
No, negative 1.
Wait a second. Hold on. Is it 2x? It's plus. It's a plus, you just can't see it. Sorry. The other one, we're going to have to fiddle with a little bit. Subtract x. Negative y is less than or equal to negative 1x added to 3. Divide everything by a negative 1. Y is greater than or equal to x minus 3. I now have two things to graph on the same plane. And this is where it gets interesting. I actually think these are kind of fun. I'm going to graph this one first. I'm graphing y is greater than negative 2x plus 1. Y-intercept, negative 2, which is negative 2 over 1. Down to right 1. I am reasonably certain that my graph is correct because it is a downhill from right to left, from left to right. From left to right, downhill is a negative slope. Okay, there's my line. We can still test 0, 0. It's not on the line exactly. So we're going to test 0, 0 right now for this one. 0 is greater than 1. Is that true or false?
False.
Thank you. It's false. I highly recommend you get out another pencil when you do these, when there's multiple to do. Okay? So this line was y is greater than negative 2x added to 1. Now we're going to do the other one. The y-intercept is a negative 3, which is right here. Slope is 1, up 1, right 1, up 1, right 1. Solid line because it's also equal to. You guys following with me here? Can we still, now pretend like this other graph has disappeared. Okay, don't look at it. Is the 0, 0 on this line? No, so we can test it. 0 is greater than or equal to -3, is that true? Yes, it is. So that means we shade the portion that includes 0, 0. So what I now can tell you is the solution to both inequalities lives in the section where both colors are shaded, which is that middle section. Blue and yellow are both shaded. So here, only this is true. Here, only that is true. We forgot to label that one. Y is greater than or equal to x minus 3. And down here, nothing's true. Last thing, example 5. And you guys saw how to do this, right? All this was twice the work for one problem. What if I give you four inequalities? Take a look at example 5. Look at their example 5. Okay? Look at their example 5. X is greater than 0, y is greater than 0. Wonderful. And then there are two other inequalities that you graphed. The blue represents the second or the last inequality. The red represents the 3x inequality. But for these two, all you had to do was recognize any x value that's bigger than 0 would work. So that's everything that way. And any y value greater than 0. So what that did was make this little portion the only truth. Okay? That's all that did. Okay, we're going to practice this some more, and in interest of time, I'm going to let you guys get started. I will do some more of these with you tomorrow.